Well, good afternoon, everyone. Thanks for being here. Um, I'm pinch hitting as MC this afternoon, and it's my great pleasure to introduce research professor Angela Marusiak. Angela joined LPL just last year in 2023. Before that, she had been at JPL, and she received her PhD in 2020 from the University of Maryland, where her thesis title was Planetary Seismology Using Single Station and Small Aperture Arrays, Implication for Mars and Ocean Worlds. So in the best tradition of PhD thesis, you're now doing something completely different science body. Angela received her BA from Boston University back in 2013. And with that, I will turn it over to you for your talk on lunar seismology, Apollo's legacy, and the new Artemis era.
Great, thank you. Can everyone hear me? Awesome. Yeah, so I initially started to put a talk together that was going to be all planetary seismology, and then we got some good news not that long ago, so I figure I might want to refocus a little bit on a body. But yeah, the moon is definitely going to be very exciting for the next couple of years, decades, as we are sending stuff back, including astronauts. So today I wanted to discuss the legacy of Apollo and what Artemis will be doing in the new era. So I'll start by doing a bit of a background on seismology, Apollo, what Artemis will be doing, the science goals, and then what that actually means for LPL and what we'll be doing here. So I have to do the obligatory seismology questions. So who here has ever taken like a college level seismology or geophysics class? Oh, okay, that's actually a little bit more than I was expecting. Cool.
And I didn't like it, but I took it.
Ouch. All right,
I'm kidding.
All right, well, hopefully this will be a bit better, and I'll do some introduction so we're all on the same page with some of the things that I discuss. Okay, the other obligatory seismology question, who here has felt an earthquake? Who here has felt an earthquake that wasn't in California? So it's kind of interesting to see, especially being in Arizona, how much that overlaps. So good, okay, at least you have all somewhat experienced ground shaking and you know what I'm talking about, at least a little bit. So earthquakes have been around for, billions of years probably, or at least many hundreds of millions. So as long as humans have been around, earthquakes have been happening. But we really didn't start to think of them sort of scientifically until around the 1st century BCE. And both ancient China as well as like ancient Greek and the Mediterranean were also thinking about these things just, because they tended to have a lot of earthquakes. So really the first scientific instrument that we know about is from the Han Dynasty, and it's a seismoscope. So this is what we think it looks like based off of drawings and previous descriptions. So the way this thing would work is if there was an earthquake, a ball would drop out of the dragon's mouth and into the frog's mouth. And it would happen roughly in the direction of where an earthquake occurred. And what this was meant to do was essentially alert the emperor or local authorities that, hey, there was an earthquake, it happened in this direction. Someone should go check it out and see how badly the damage happened, or like if people are hurt or need help. So it couldn't tell you magnitude, it didn't record really ground motion per se. It was just mostly like a danger beacon that you can kind of think of. And then it really wasn't until the 19th century that we started to have sort of modern seismic equipment. And the reason for this was a large earthquake in Lisbon. So Lisbon is on the coast of Portugal. And what happened is there was an earthquake off the coast. So they got hit with lots of ground shaking. And then because the method of keeping things warm and keeping things alight was basically like oil, lamps, and candles, there was a huge fire, which was a very common follow-on to a lot of earthquakes at that time, and even up until the 1900s. And then to make matters even worse, because it happened offshore, there was a tsunami. So Lisbon was almost completely destroyed. And at that time, it was a really important city for trade and for other things going on. So it kind of led to a lot of people thinking, all right, we're in the age of enlightenment. What can we do to better study these phenomenon? They were thinking, can we predict these? Can we, evacuate a city ahead of time? Is there a way that we can, build our buildings differently? Or what can we do so that, a massive tragedy like this doesn't necessarily happen again? And that's how we ended up with the first sort of seismographs at the time. And then not too long after that, when we started to actually record these waveforms, we start to see some patterns kind of emerge. And around the early 1900s, late 1800s, people actually started to do seismology as a science. So what has that done for Earth? Well, one of the first things that we can look at is seismicity. So up here, I have plotted all the events that happened last calendar year that were above a magnitude 4.5. What's also plotted on here, and might be a little hard to see, these red lines are plate tectonics. And they're hard to see because they tend to get covered up with events. So of note, the bigger the event, the bigger the circle is what that's indicating. So it's very easy in the year 2024 to look at this and say, oh yeah, duh, there's plate tectonics. But this ended up being a really key piece of evidence for the theory of plate tectonics, because when we started plotting out where earthquakes happen, we realized it's not really that random. The bigger earthquakes tend to happen near subduction zones. Of course, last year there was the devastating large quake in the Syria-Turkey area. But if you look at like the mid-ocean ridge, they're not quite as large in magnitude. If I was to plot up depth, what you would also see is like California is very shallow. Again, spreading centers are very shallow. But then subduction areas, you can have very deep quakes. And these are actually occurring as the subducting slab goes down. So seismology was one of the really big pieces of evidence that Earth is actually split up into plates and it's moving. So really, really important for geophysics and for geology in general. Now, in addition to these large naturally occurring events, you can also have induced seismicity. So this is a plot, same year, 2023, for magnitude 2.5 that happened in the US. One of the things I want to bring your attention to is the third largest event. It's in Texas. Texas is not known to have plate boundaries. Anyone want to guess why Texas has a...
Fracking.
Very close. Not actually completely right. Fracking does induce some earthquakes, but it's actually the wastewater injection after fracking that causes these events. It's kind of nitpicky. What you'll also kind of notice is Ohio has some events, especially like right on the border of some states, but like Pennsylvania doesn't. Pennsylvania allows fracking, but doesn't allow wastewater injection, and Ohio does. So if I was to plot down even smaller events, you could see the border of Ohio and Pennsylvania. Also notable, Oklahoma also has a lot of seismicity, and yeah, you can see the concentration in, shouldn't really surprise anyone, West Texas, where there's oil fields. If you're an eagle eye observer, you might also notice there is an event that is not far from Tucson. So back in September, we did have a magnitude, like I think it was a 4.3-ish. So if you happen to feel shaking sometime in September and thought that was kind of weird, you probably felt that earthquake. You might also notice there are some triangles on this map. Those indicate mining blasts. So when you're trying to mine and expand your shafts deeper, you can use explosives, sometimes legally, sometimes not. But those get registered on the USGS catalog, and they can sometimes cause quite a bit of shaking. Some other types of events that we can sometimes see, so not just like mining explosions, but nuclear explosions. So one of the reasons that we have so many seismometers spread out around the globe and the global seismic network, if you notice the dates that they get deployed, it's right around the time of the Cold War. And that's because we did not trust Russia to not build nukes after we said, yeah, no one's going to build nukes anymore. So we basically instrumented different parts all around outside of the Russian boundary, but near Russia and other parts of the globe, in order to essentially see whether or not people are doing nuclear tests. and it's actually still ongoing bits of research. So every couple of years, we'll notice North Korea has an event. They will say sometimes that it's a certain size, but when you look at the seismogram, it tends to indicate that they might not be completely truthful in what they're actually capable of, which is always kind of fun. Some other events that you can get are things like avalanches and rock falls, or things like ice quakes. So Danny, Hop, Veronica, and I have been working on a project where we were testing seismometers out on a glacier. And one of the most common types of events we were seeing was the ice cracking and breaking. So this is an area of research that's really important for climate change, because we can instrument things like the Ross Ice Shelf and see how it's potentially breaking up. We can also instrument glaciers. And if we think there's evidence of a glacial outburst flood, we can warn people that are downslope that they might need to evacuate. So seismology today continues to inform us a lot, and also, potentially make us a little bit safer. So what do you do once you have these events and you have seismic waves? Well, you can interpret them. So to get everyone on the same page, there's essentially three main types of seismic waves. You have body waves, which travel through the body. Seismology is not very clever with their names, so a lot of times it's pretty easy to figure out what we're talking about, which is kind of nice. So for body waves, you have two main flavors, P and S waves. P stands for primary or compression, depending on who you talk to. Those are seismic waves that will propagate in the direction that they're traveling in, so they tend to move the ground vertically a lot. The other type are shear waves, which they propagate perpendicular to the direction that they travel in. So they tend to excite what we call the transverse component the most. Then you have, I'll discuss this in a little bit. As you bounce off different layers, we tend to get fancy with names. So if you bounce off the core, you might be a shear wave that hits the core and comes back as a shear wave, so SCS. If you bounce off the mantle, you'll be like a PMP or SMP, something like that. And that just kind of indicates the travel paths. Maybe this is why you didn't enjoy your seismology class, but possibly you were presented with a picture like this where you had to identify all the different seismic waves. And especially if you're dealing with something that goes through the inner core, you might end up with something crazy like PK, IKP, IKP, things like that. Professors love to do that just to tease their students a little bit. So in addition to body waves, you have surface waves. As the name suggests, these travel along the surface of a body. So you can have Rayleigh or essentially love waves are the two most common ones that we see on Earth. So Rayleigh are a mixture of, or they are compressive waves. And they have interesting sort of like backwards rolling motion. And then you have love waves, which are only shear waves. So again, these won't really propagate through a fluid because you can't generate shear motion in a fluid. The last type of seismic wave that we kind of look at is what's called a normal mode. So these things are really only seen when you have very large events. So really there's only maybe one or two events a year that we can actually look at normal modes. And you can kind of think of it as like you're ringing a bell. And they're really great at being able to constrain like deep interior. But because you need a really large event, they're not super useful for most planetary bodies because without plate tectonics, it can sometimes be hard to generate large seismic events. But they can be observed for up to a month because they're very long period waves. One last thing I want to point out when talking about body waves, because this will become important for the moon, you can end up with shadow zones where as your seismic waves are traveling, they hit the core. And because the core has a different velocity than the mantle, they end up bending and refracting. So even though seismic waves might enter or interact near the core at a similar point, you end up with a quite large shadow zone where you actually don't observe them. And I'll explain why that matters for the moon in a little bit. So one of the questions I get asked a lot as a planetary seismologist is, what can you actually do with a single station? And I like to remind people that, back in the early 1900s, that's essentially what we were working with, is we had very sparse networks. We were really only able to record very large events. So essentially, we were working with single station stuff. So even with that, we were still able to look at deep structure. So for example, in 1906, Oldman was able to constrain the size of the core by looking at where did you have P waves and where was the shadow zone, because he noted that as they bend through the core, they would end up with a unique pattern where you would have these sort of blank spots. So I think he actually got within like 10 kilometers or something, like really good of what our outer core actually is. You'll note that there's no inner core. That would not be discovered for a little bit later by Inga Lehman. So she noted on seismograms that there was this phase that she kept seeing at certain distances, which she called P prime. And to this day, that is the shortest title of a paper I have ever seen. It's literally P apostrophe. That is the length of the paper title, which makes it incredibly infuriating as a grad student to look up, because you see that and you're like, well, clearly that's not actually the name of the paper. It is. So through seeing the inner core and being able to do things like travel times where you note, like this is only looking at 3 seismograms, but seeing where the P wave is or isn't observed and how your surface waves move, we were able to learn a lot about Earth. And of course, as you get better and better data, because you have more earthquakes, you have more seismometers, the seismometers get better, we can essentially image the Earth, not unlike an ultrasound or sonogram. So this is from Garnero and McNamara back in 2008. But what they show is we can see things like LLSVPs, mantle transition zones. We can see these relatively small, ultra low velocity zones. Here they are showing a subducting slab going down all the way to the core mantle boundary. There's some other features here as well that they're pointing out. And the way that they're able to do this is by looking at like seismic reflections off of these different features. But also noting where you have relatively fast, which is the blue, or relatively slow seismic velocities. This type of approach is often referred to as tomography, but it allows us to really image the Earth in a way that we would be unable to do otherwise. We can do things like gravity, or for the Earth, we can do geochemistry measurements at the surface. But through seismology, we're really able to connect what's going down at the core mantle boundary or what's going on in the mantle, and how does that affect what we're seeing at the surface. And it's worth noting that on a smaller scale, we can do this as well and like look for things like oil and gas reservoirs, or every couple of years, people feel the need to like re-image Yellowstone and like talk about the magma chamber and what that means. And even if they say something completely benign, some news organization will say, scientists think Yellowstone's going to blow any day. And then people have to write and be like, that's not what the paper is saying, like at all. Please stop doing this. But yeah, so hopefully I have shown you that seismology has been really, really important for the study of geology and geophysics on Earth, and also for helping us be a bit safer. So it kind of makes sense that as we go and explore our solar system, this is going to be one of the methods that we want to take with us. And that's what happened with Apollo. So all of the landed Apollo missions had seismometers. So Buzz Aldrin, Neil Armstrong were the first ones to install a real working planetary seismometer during the Apollo 11 landing. And then Apollo 12 through 17, not including 13, if you don't know why, there's a really good Tom Hanks movie explaining why, built up a seismic network. What you'll notice is if you look at where the stations are located, they're all on the near side and they're roughly equatorial. 15 and 17 tend to be a little bit further away, but they're still within 30 degrees. There were both active, meaning explosives were set off, or like we knew an event was going to occur, like the lunar module leaving, and then passive experiments where we basically like chilled out and wait for moonquakes to happen. But there were a lot of key findings. So namely one, the moon is actually differentiated. So it does have a crust, mantle, and core. Still debated today a little bit. Do Do you have a liquid outer core? Is there a partial melt layer? And also, is it actually homogeneous, or is there something weird going on? Because as I noted before, you end up with shadow zones, right? So if all of your stations are all on the near side and relatively close together, you're going to end up with a shadow zone on the far side where you're not going to be able to see if something like a deep moonquake is happening there, because you're essentially blind to it. So we don't know a lot about the deep interior of the far side because we didn't have instruments there. So that's another reason I'm very excited for Artemis coming up. So deep moonquakes were one of the most common events that occurred. So here's like 3 examples of what they look like. If you're not a seismologist and these just look like really bad squiggles to you, that's not surprising because that's really horrific data. Like that is something where if we recorded that on Earth, we would just throw that out and say like there was a bad glitch. Like we would not want to use that. Part of the reason is the moon is very scattering. So its mega regolith, it doesn't lend itself to clean arrivals. The other part is these seismometers were 8-bit. So they're very blocky in nature for that reason. They don't have great temporal or spatial resolution. Their sampling rates, something also was kind of funky with the atomic clocks that they were using. So the sampling rate is not as consistent as it should be, which again means that your timings are off. So when we detected the lunar core, which only happened seismically really in 2011 in terms of defining its size well, what they had to do was stack, so like literally add on top of each other different seismograms. So this is an example of what happens when you add 50 different seismograms on top of each other. It helps that these moonquakes tend to happen in clusters, so you can do it cluster by cluster. Even this is really not superb. Like I would have a really hard time saying which of these peaks is actually P and where exactly does S start. So what they went ahead and did is a lot of filtering, a lot of signal processing analysis in order to end up with this, which is not bad. It's definitely an improvement over this, but like considering all the work that had to go into it, it's not ideal. Oh, that's not good. They apparently did not like me bad-mouthing their seismometers. The ghost of Apollo were chasing me. Where was it? Oh, so in addition to deep moonquakes and internal structure, one of the other things that they were able to constrain is the modern impact rate. So we were able to say, this is how often the moon is getting hit with impacts. And then from that, and knowing the ages of different cratered regions, we can kind of back out what we think the impact history was. And this is important not just for the moon, but it led to a lot of the crater counting that goes on today. Because we have the moon benchmarked pretty well when we go to places like Europa or Mars and we see impacts, that's how we're partially how we're able to like come up with rough ages for things from craters. And while there are no plate tectonics on the moon, there are shallow events. So these shallow events are basically caused by as the moon gets older, it gets colder and it shrinks. So if you've ever had like an apple or like a peach that maybe has gone too ripe, you'll notice it gets like wrinkle ridges on it. The moon is very similar. It has lobate scarps and wrinkle ridges. And as these features form from the contraction, you end up with seismic events. And these events can actually be quite large. And in a couple of slides, I'll show you how they're modeled. But if we want to head back to the moon with people or potentially make ourselves a little bit more of a permanent presence there, we're going to want to consider, are we dealing with the seismicity of Texas? Are we dealing with the seismicity of New Jersey, where, God forbid, you have one event, everyone in the news talks about how New York is in danger because no one actually cares about Jersey, which is sad. Where are you falling on the risk sort of spectrum? But yeah, and in case I did not hammer that home enough, and please don't curse me again, yeah, data, not the best. So in the modern era, there's a lot more opportunities for us to now go back and build off of Apollo's legacy. So learn, what they had shown us originally and go and address a lot of those questions that we still have answered. So one of them is through the commercial payloads program. So in 2025, there is a PRISM with CLIPS called the Farside Seismic Suite, FSS. So that is this guy here. To give you a sense of scale, he's about 40 centimeters by 40 centimeters by 40 centimeters. So he's not, too big. I don't know why I'm gendering him. The PI is Mark Panning, maybe that's why. So it was selected to fly in the South Polar area in Schrodinger Basin specifically. What it is built off of is essentially the flight spares of InSight, which was the mission to Mars that was very successful. And I was very fortunate to be part of for my PhD and postdoc. But yeah, InSight was very expensive. It was very good, but the instruments were expensive. So we're going to reuse the flight spares for the moon. So it's going to contain 3 components of the short period seismometer. So it'll have like the 3 orthogonal directions, but it'll only have the vertical component of the VBB. That's because we only have so many of the VBB components because they're so expensive to make because it's so sensitive. So we didn't want to send them all on CLIPS. So like I said, this one should launch in 2025. If you haven't been following the news, the CLIPS program has had some partial successes and some not successful things. So hopefully by the time Farside Seismic Suite goes, it will be successful and not tip over. So my postdoc advisor is Mark Panning, who is PIing this. And I do like to tease him occasionally that our sensors are tilt intolerant. So if you tip us over, we still work pretty well, which Intuitive Machines, I think, is rather interested in after their slight issue with the last CLIPS. But what I'm really, really excited about to talk to you all about today is Artemis. So Artemis is really the modern equivalent of Apollo. So we already had the first one launch. That one was to prove that essentially the rocket that we want to use works. Artemis 2 will be a crewed flight around the moon. So somewhat akin to Apollo 10, if you follow the Apollo history. But Artemis 3 will be the one that will actually put boots on the moon. And it won't just be white men doing it. It'll be women are finally going to the moon. A person of color is finally going to the moon. And we're also going to be sending a non-American as well. I think right now it's slated to be a Canadian. So it's really exciting that in this modern era, like the moon is for everyone, not just people who like served in the military. Again, please don't curse me for saying that. But Artemis has several science goals that they outlined that they would like us to achieve. And I've highlighted in yellow the ones that a seismometer should be able to achieve. So I've already kind of shown how like differentiation can be done through seismology. And what we're hoping to do, since we're heading to the South Pole, is be able to answer that question, is the near side and the far side similar? Or is there some heterogeneity going on? So we know that the surface of the moon has this sort of dichotomy to it. The near side and the far side are not identical. So we're kind of curious to see how far down does that actually extend? Like, is this something that's just limited to the crust and is caused by impacts? Or is there something going on in the mantle or maybe even deep down towards the core? One of the other things we'll be able to do is help interpret the impact history of the Earth-Moon system. So at the south pole of the moon is the Atkin Basin, which is a very large impactor. So we're going to be somewhere along the edge of it. They haven't told us exactly where our landing site is going to be, but they're all roughly in a similar area. So what we should be able to do is measure things like how thick is the injector blanket? Is there any remnants of that large impactor in the crust or in the mantle that we can image? Can we sort of confirm or work with the Grail instrument at all to be able to constrain deeper down? And then lastly, is investigating and mitigating those exploration risks. So by deploying our seismometers, we should be able to address how much seismic shaking do we actually see? Is a magnitude 4 or 5 possible? How often does that occur? Is it something that we want to take into account as we build buildings or as habitats go up? Is it something we need to train the astronauts to do? Like, do they need to do earthquake drills, moonquake drills? Or is it something where this happens so rarely that it's, hey, this might happen, but don't worry about it. So that brings me to seismology at LPL. So just about a month ago, we got the good news that LEMS was selected to fly with the Artemis deployed instrument. This is being PI'd out of UMBC and Goddard. But UA LPL will be the ones that are actually supplying the seismometer for the instrument package, which is very exciting. And this has been work that's been going on for nearly a decade with our partners at Silicon Audio. So we have been developing this through things like the P-STAR program, which does analog field work, which is where all these lovely photos come from. It's also been through the IC2. So originally when we started developing these for flight, we were thinking about sending them to like Europa as part of the Europa Lander project. So we got some funding to make sure our instrument could work at cold temperatures, hence why we were also in Alaska and in Greenland to do the work there. And then we also more recently have funding through Dolly and Matisse. So Dolly is focused on lunar aspects, and the Matisse is actually a pretty cool project where we're looking at how a seismometer on a binary asteroid could be used to look at things like interior structure. So before I move on too much, I want to put in a little context this photo up here. So that's me standing next to Danny. This was about 3 months after I defended my PhD thesis and became a PhD candidate. So right before I did that, I was at a workshop for cryoseismology, where it was like basically all people that study glaciers and ice caps, and I was the only planetary person. So it was sort of a running joke that when people were comparing their different field sites, mine was sort of the best and worst because I just worked from my computer, because all my field sites as a planetary person were, millions and billions of kilometers away. So clearly there was no chance I was going to ever end up at my field site. About a week after that workshop, I spent 5 hours, which is not an exaggeration, defending my proposal that was focused on modeling. So I was convincing my committee that over the next 3 years, I was going to sit in my nice climate-controlled lab and do modeling work to show what seismograms would look like on Europa. About a month after that, my advisor came into the lab and said, hey, we got a P-STAR funded through the University of Arizona. He's like, do you want to go to Alaska? And I was like, oh, it's August and September. That's a great time to visit Alaska. Yeah, that's September in Alaska. It's cold and it's snowing, which also, fun fact that he didn't tell me, finding cold weather gear in Maryland in the summer is not trivial. So thank God for Amazon. So I bring this up just to remind grad students and early careers in particular that you might have a really great idea of what you think you're going to be doing over the next couple of years. But you never know when an opportunity is going to come by that allows you to go to really cool places, pun intended, and could end up with a faculty position like 7 years later. So I say that to bear in mind that sometimes the crazy ideas that your advisors come up with actually do really benefit you. So anyway, back to Artemis and the moon. So one of the things that makes Artemis really unique is the fact that it's going to be astronaut deployed, which really only has happened with the Apollo era. So everything else has to be robots. So what that allows us to do from a seismic perspective is to actually not just be on a lander deck like the CLIPS missions are going to be, or on the ground like InSight was. We can actually be buried. So our SP is pictured here. That's the short period seismometer. So if you're having a hard time reading, it's about 50 millimeters by like 120 millimeters. It's smaller than this, essentially. So what that allows us to do is that when the astronauts are taking geologic core samples, they can stick us at the end of that drive tube and basically shove us down that hole, which will allow us to be buried 35 centimeters, potentially even deeper, depending on how well that drive tube actually works, which is really great because that means that we're going to be thermally insulated. It means that we're going to mitigate against some of that scattering effect that I was talking about. So our signal quality is going to be much, much higher than Apollo was. We're also going to be sending a very broadband instrument. So this one is more sensitive, but it's also a bit bulky. Each of its 3 components is like that big-ish. So it's in total a bit bigger. So instead of making them dig a giant hole, like my PhD advisor would probably make me do, we're going to have them put a trench in instead. So that one will be a little bit more shallowly buried. And it'll be buried so the long way is horizontal. And there's a couple of science goals that we're going to try to address while we're there. So one is going to be to characterize lunar seismicity. So to be able to say, what do we detect and what does that tell us about the moon in and of itself? Not unlike when we look at Earth seismicity, what does that tell us about like tectonic history or human activity? Using that seismicity, what can we learn about the internal structure, specifically at the South Pole as well? So like, can we image the old impactor? Can we see what's going on the deep side of the moon? And then also assess the local and global seismic hazards. So be able to say, at the South Pole specifically, this is what the ground shaking you might appear. And based on where, impacts or shallow events are happening, here's maybe an area that's a little bit more active. So maybe we want to like not put our humans there. Maybe we want to go where it's a little bit quieter, pick a New Jersey over a California, so to speak. And the way that we're going to be able to do that is by looking at both the SP and the VB. So the SP is in red here and the VBB is in blue. The way to read this is that anything that falls above this line, we can see. Anything below the line, we probably won't be able to see. Of note is the geophones from Apollo and the short period from Apollo as well. So you can see we're doing a lot better than both of those instruments, which means we should be able to detect a lot more. So some of the things we expect to see are like those tidally induced moonquakes. So as the moon is going about its orbit, it creates tides here on Earth. We get our revenge, so to speak, by generating those deep moonquakes. We should also be able to see near surface structure, sort of active seismicity and impacts, which is how we'll be able to look at like things like the impact rate and be able to begin to answer questions about tectonics. What you'll also note about these events is they don't happen in the same frequency space, which is how we'll be able to identify the different types of events. So note here that these amplitudes are not the same scale. So to start with deep moonquakes, their amplitudes aren't that big, which kind of makes sense. Like they happen deep down in the moon. They got to travel a long way before we can actually register them on our sensors. But notably, their frequency content is really quite low. So they're all the way down here below a hertz. Compare that to an impact, which now has, roughly the same amplitude. And, you'll be forgiven if you think these two panels look the same. But when you look at their frequency content, the impact does have a lot of higher frequency surrounding it. So like if I was given these two seismograms and these two spectrograms, I would be able to say which one's an impact and which one's a deep moonquake. Shallow events have much higher amplitudes, which makes sense. They're relatively close to the surface. They can be quite large. So they're going to create larger ground shaking for us to see. And they also have a really unique sort of L-shaped shape to them. So this sort of change from high frequency to low frequency, we call like surface wave dispersion. And it's one of the things that we can use to look at things like crustal structure. But you'll also notice that in general, they also have like this low frequency content, and their timing is also a bit longer, more akin to like a deep moonquake than the impactor. The last type of events are thermal events. So these are caused at the surface as the moon rapidly heats up and cools. It stresses the environment, so you can have boulders kind of crack And if you have equipment left in the field, like say from your lunar module, that will also crack and shift as you go through the lunar day and lunar night. So these have frequencies that tend to be right at about 10 hertz if they're naturally occurring. And as you can tell, like their amplitudes are not necessarily the best, but like they stand out over this background. The lunar module, their frequency content ranges a little bit more, and their amplitudes can also be quite high. So not only can we distinguish a thermal event from, say, an impact or a shallow event, we can also say, is this like a naturally occurring thermal event from, say, like a boulder, or is this from equipment that was left behind after the astronauts left the surface? So we're going to be deployed for nominally 3 months, but we'll have the capacity to go for up to 2 years if NASA deems us worthy enough of funding, which hopefully they will. So we've looked at how many of these events should we actually be able to see. And this is roughly based off of what did Apollo see. So if we were to like re-land over 3 months, how much events did Apollo see over the same time period, essentially? So for deep moonquakes, we should be seeing at least 100 to 200 over 3 months, but we could see well over 1,000 over 2 years. For impacts, it's probably going to be a bit less, tens of events over 3 months, maybe a few hundred over the 2 years. And then for the shallow moonquakes, that's a bit more uncertain because we see these low base scarps. We know there's evidence that Apollo recorded seismicity, but now that we're actually in the South Pole, where we're closer to where some of these events were occurring, we'll have to see how that actually changes things. So we may not see any at all over 3 months, but if we do get our 2 years, then we should be able to start to see some of these events. So it's worth noting that just because we're recording, like say 1,000 deep moonquakes, it doesn't mean we're necessarily going to be able to use the waveforms of 1,000 deep moonquakes. If we are having trouble locating them, or if they don't have really high signal to noise ratios, we might have enough info to classify them and say when they happened, but we may not be able to use them. So based off of InSight and other analog field work, we estimate that really only 10% of the events we actually record are going to have sufficient quality for us to be able to use further. But there's a lot of stuff that we can do with that. So one of the things we can do is look at crustal structure. So we can use things like vertical autocorrelation or radial receiver functions to start to back out what is the structure of the crust. So we can look at things, and this is what I was saying, where sometimes the nomenclature for body waves can get slightly complicated. So you can have something where it's a P wave that goes through the mantle and bounces. So it's a PMP. You can have something that's a P wave, hits the mantle crust transition, comes up as an S wave. So that's a PS. You can get things with multiple bouncing. So you can get 2 Ps followed by 1 S. But if you were to look at these arrivals on a seismogram and compare them to an initial arrival, you can see how they move out, and you can use essentially the timings of these with the velocities to figure out what is this height here. It's essentially like a distance equals rate times time situation, where you can figure out the timing. We roughly know the rate, so we can figure out the distance traveled, do some nice trigonometry. So you can all tell your geometry teachers from high school that yes, the Pythagoras theorem does actually get used in real life. It comes in handy here to figure out what the crust looks like. So this is sort of a simplified version, but what we should be able to see is stuff like large scale basin ejecta from the Atkin Basin. We can see where the crust is disturbed, where we have some fracturing, where we have pristine crust, and then about how deep is that crust mantle transition. We can do a similar thing for the core. So when I was a PhD student, The project that I actually focused on before I started working with the folks at Arizona on the instruments was core detection. So the primary way that we do it is looking at a phase called SCS. That's a shear core shear wave. So essentially what that looks like. Now keep in mind, you have a deep moonquake, so that's why the center is a bit lower in the lower mantle. But essentially what you have is a deep moonquake will happen and you'll have reflections off of things like potentially a partial melt layer, a core, and then your inner core. So yeah, that SCS would be the one that bounces off the inner core. SPM, so partial melt, would bounce off the partial melt. And then if you're traveling through the inner core, or excuse me, through the outer core, which is K, bouncing off the inner core I, that's how you end up with PKIKP. So the names get a little bit confusing at times, but essentially what you can do is look at the travel time move outs of these different waves on, you know, your vertical, radial, or transverse component. And from these move outs, you can figure out how big are these layers and how thick are these layers. And from the work that I did with my PhD, it takes a surprisingly few number of events to do that. It really only takes 5 or 6 events if you can locate them quasi well in order to be able to pull the core out. We also know this from InSight. So while I was a PhD student and postdoc, we investigated the size of the Martian core. So essentially what we do is we can look at a spectrogram, or excuse me, seismogram. So this is for Mars. So you can see how when you have more updated instruments, your seismograms look a lot prettier. And we can identify where we think the core reflected wave is arriving, both on like individual events, which is what this is, or when you stack them together. And then you can compare them to different models and how coherent that stack and a peak is. So what we were able to do is compare like hundreds of different models of the Martian interior. And we found models that were able to create really nice, strong peaks where we were expecting to see SCS. And then this is actually one of the plots that I contributed to the paper, where you look at what is the predicted time of arrival versus when did you actually pick SCS, which if you're the only one on the paper or you have a small team is pretty easy to do. When you have like 40 co-authors and they cannot agree on a pick, it becomes slightly more challenging. But essentially by just looking at model prediction versus offset, that's another way that we can see you have smaller offset at a similar core radius to what we were able to grab. So from this paper, we were able to take an uncertainty in core size of plus or minus 200 and reduce it down to like plus or minus 40. And subsequent papers have also come out afterwards that have even constrained that even further. And this was using only 6 events from Mars. So if we have plenty of events from the moon, we should be able to do this no problem. So the last goal of LEMS is going to be looking at seismic hazards. So as I mentioned, there are some lobate scarps in the area. So the blue is all the different landing sites of where Artemis is. The yellow are these lobate wrinkle ridges where seismic events could occur. And the green stars are from Apollo, where we have known events. So what we were able to do is actually, take an event, look at what we think its moment was based on Apollo, and be able to measure seismic shaking. So this is in terms of acceleration. So you can see, for about Earth's gravity, you'd be in this range. So for a seismic event, you could potentially end up creating shaking on the order of Earth's gravity. And what that means is when you're at 1 lunar G, you can end up with strong or moderate shaking, depending on how far away you are from the event. If you happen to be within like 10 kilometers, that actually goes up to severe and violent shaking. So when we talk about seismic hazards on the moon, even though we don't have plate tectonics, if you're experiencing violent shaking, that's something you're going to want to know about. And you're going to want to know, is this something that's going to happen once a week, once a month, once a year, every 10 years? Like, how concerned do we need to be about this? So there is some future work for LEMS. One of them is that we are doing TRL testing for the VBB. So just last week, we passed our vibrational testing. Based on the fact that Veronica's in the audience, I assume TVAC is going well.
I'll talk to you afterwards.
Oh, God. That's always what you want to hear. That's okay. So yeah, environmental testing is ongoing. So with our existing prototypes that we're testing right now, we're hoping that they can essentially serve as our engineering test models. So when the astronauts need to learn how to like install our instruments, we can actually send them prototypes that do work instead of just like, you know, a 3D printed mass model. We are going to end up building new SPs and VBBs that will actually head to the moon. We are hoping to use the nice new ARB building, assuming all of their facilities are up and running by the time we need it. So again, hopefully when we do environmental testing again on those flight sensors, they can be done at the ARB and pass without too much issue. We do also need to train the astronauts to let them know, like, this is how deep we expect you to go. This is how you turn on our seismometers. This is, you know, all the installation process. So some of us will be down at mission control to make sure that everything is installed and good. Once we get to that point, we actually need to deliver our flight sensors. And as of right now, we are scheduled to launch in September 2026, although that is probably going to slip even further. But then there's some non-LEMS work that we're also going to be doing. So as I mentioned, we have some binary asteroid work that's ongoing. So we're going to be doing some testing on those instruments, which are really similar to the ones on the moon, and be able to assess, you know, what types of seismicity can we see there. Although based on preliminary measurements, we should be able to see the tidal interactions from that binary. We're probably going to be proposing to future flight opportunities. So things like SALSA, PRISM, Artemis 4. And essentially, we're going to see if we can maybe backdoor our way into building up a lunar geophysical network. And then I also do icy ocean world science for the Dragonfly mission. So when I'm not thinking about the moon or worrying about what's going on with TVAC, I think about what does seismology on Titan look like. So with that, I'm happy to take questions. And I do just want to acknowledge that, you know, this is all a collaborative effort. So it's not just me alone doing this. Danny, Veronica, and Hop have been working on this, you know, for years while I was a grad student. And then, yeah, we have lots of great folks at LEMS, including actually my former PhD advisors on the proposal. So yeah, I'm really excited for what Artemis can do, and I'm super thrilled that LPL gets to be a part of it.
Thanks, Angela. When you were talking about like the seismic hazards, we always learn like the magnitude scale as a scale of energy. Does that map directly to the moon, or does the moon have to have its own scale, or how does that?
No, it does roughly map. So the idea of following like a Gutenberg-Richter line is how we typically think of it. Like, how often do the events happen, and how does moment magnitude convert to actual magnitude? Those are all like physically linked, and gravity doesn't really come into it. Where gravity comes into it is basically, how does that actually translate like on the surface in terms of like what you feel? Because if you have 1/6 the gravity, but you're shaking at Earth's gravity, or the ground is accelerating at Earth's gravity, it's going to feel a lot more violent than if you were on Earth. So that's really the only difference that happens there.
In California, we were all trained to go after an earthquake to go to the USGS. Did you feel it?
Yes.
Side and click how strong this shaking was? We're going to need something like that on the moon. Questions for Angela? Tom?
I actually did enjoy my geophysics class, just for the record. You know, there was an earthquake in New Jersey recently.
I do, yeah. I still have some family there, but it was really interesting for me. to kind of just see how all the articles were like, New York City experiences shaking. And it's like, it did happen in New Jersey. Like the state is inhabited. Like it's not empty during the day. We don't all just like go to New York. Like if you want to see like damage, like go there. Like I understand New York City is like an important city, but like New Jersey's a state too, guys. But yeah.
Yeah, it's, my brother wouldn't stop talking about it. Anyway, but I have a question for you, which was, I think one of your slides you showed like the number of seismic events on the moon.
Yeah.
Was it fair to say that deep seismic events tend to be the most abundant, or?
With the exception of thermal moonquakes, yeah.
Okay.
So we didn't plot up thermal moonquakes here. Thermal moonquakes, their cadence is also based on like the day-night cycle, and you can have like thousands happen in one day. So they will technically outnumber deep moonquakes. But yeah, the reason we like deep moonquakes is that they tend to be bigger in magnitude and not as close, so that we can do things like this and this. Whereas with a thermal event, because they're small and local, they may not travel far enough for the seismic waves to really bounce down and have good amplitudes for us to use. So they're really great for local structure, but for looking at like the deep mantle, they're not quite as useful.
Do we have a sense what they're due to? Why they happen, these deep?
Yeah. So there were a couple of papers that recently came out. So when you look at when they happen compared to the temperature and the change in temperature, that's how we're able to say like they're definitely a thermally driven event.
Okay.
With Apollo, they had a small geophone array. And what people have done is actually look at like where these events happened. And most of the events point right back to the lunar module. So we think it's not exactly a coincidence that they all tend to originate from that lunar module, or not all, but many do. So the best theory that we have is, yeah, like metal will, when it changes temperatures, can act funky and, you know, kind of crack and creak. And that's essentially what we're seeing. There is also a hypothesis by a certain Apollo astronaut that some of the other events are originating from, how do I want to phrase this? Human waste left on the moon. So yeah, poop quakes are apparently potentially another source. I'm not sure I entirely believe that, but he's an astronaut, maybe he knows.
It's worth noting that NASA turned off the Apollo seismic network to pay for space shuttle. So the tension of science and exploration is an old story. Any other questions from the audience?
At what depth do you start considering them deep earthquakes?
The deep moonquakes typically happen really far down in the interior. So there's not necessarily like a specific cutoff. It's just, you know, are they happening deep here or are they at the surface? So there's sort of an in-between layer where like events don't really happen. So you're either really shallow or you happen deep. It's like on the order of like several hundred kilometers down.
Sukru?
Thank you very much for a great talk. I was wondering if you could talk a little bit about some of your future work. In particular, what are some of the science questions you hope to answer with seismology on Titan?
Oh, okay. Yeah. So on Titan, one of the things we're really interested in is the fact that it has a subsurface ocean, and its icy crust is kind of unique. So unlike Earth, where our ice is all water ice, on Titan, it's probably a combination of water ice and methane clathrates. So a lot of my postdoc work focused on can we actually look at how seismic waves propagate through a clathrate layer to be able to figure out, does clathrates exist and how thick of a layer is it? So I'm really excited to be able to land there and see if we're able to do it. The finding actually was, yes, the clathrate layer will affect seismic waves and seismic velocity structure, but it's on the order of about like 5 to 8%, which when you're looking at seismic velocity structure on the Earth is easy peasy to do, because we have thousands of events and seismometers. But for like Mars and the moon, 5% is where your rough uncertainty is. So I'm kind of interested to see, like, could we see that clathrate layer? Is it there? Is it not there? And then in general, just kind of looking at like, what does seismology look like on a world where you have a free floating ice shell over an ocean, but also a really thick atmosphere? I think there's going to be a lot of sort of surprising things that we may not anticipate. So I'm kind of interested to see like what that might look like. Like, what did we not think to potentially consider? Because that always tends to happen in, you know, some missions. You can account for like, here's all the science I think I can do, but normally there's always one or two curveballs and fun things that you find. So that's what I'm really excited for. And that mission will be launching in 2028 or 7, and should be arriving in like the mid 2030s. So hopefully I will be done thinking about the moon and can think about a different moon at that point.
And finally, let's take the last question from online, and it's about the far size seismic suite. And since it's not deployed to the surface, is the things you were just talking about with the lander, thermal cycling, is that an issue for that?
Potentially. So some of the work that you know, we've actually already done at LPL. So if you notice in the one fieldwork photo I included, where is it? Here. So when we deployed, that seismometer is on a mock lander. It's hard to see, but there's also one underneath it. There's another seismometer there, and we have some on the legs. So part of my PhD work was actually looking at those different configurations and how does the seismic waveforms and things like measuring background noise and recording seismic events change. The reason it was in a vault is so that we could be, a bit more thermally insulated and not have to worry about wind as much. So what we essentially found is, generally speaking, this quality is still good. Like many of the events that you could use when you're on the ground, you can still use when you're on the lander. That being said, there was a resonant frequency of about 75 hertz that we were seeing. And you could also see it on the waveforms a bit. So you didn't have quite as crisp of rivals with the lander. It sometimes waves would interfere with each other, or like it would be hard to identify them because they'd overlap a little bit. So Farside Seismic Suite, you should still be able to get a lot of great science out of it. But yeah, the lander is definitely going to introduce its own intrinsic noise. And then of course, if they are also heating up and cooling, it's very likely the lander itself could also be experiencing or creating thermal moonquakes. So on the one hand, you're basically zero distance from the source. So you're going to have really high amplitudes. But I'm kind of curious to see how that might affect other seismic wave analysis, because if you have these events happening, you know, it's 1,000 times a day over like day night, you know, so they're happening very, very frequently. Is that going to end up blocking some of the other signals you might see? So Mark Panning and I have had some discussions back and forth about like how much can you actually see, and it's important to keep in mind any seismic data is better than no seismic data. So it's not to say like, oh, FSS is going to be worthless because we're sending Artemis. It's still going to be incredibly useful. But yeah, the lander is a consideration and definitely a source of noise.
All right, well, thank you so much.